In the last section, we dove deep into how to do testing and benchmarking in Go. In this section, we'll discuss how to use Go to manipulate files and decipher serialization formats like JSON, XML, and CSV. So we'll start by discussing file handling in Go. We'll then jump into JSON format handling in Go. Then from there, we'll cover XML, and the last video will cover CSV in this section. Let's get started. We'll start with the first video in this section, which is file handling in Go. We will learn how to open and create files, and then we'll do some basic operations like move, copy, and delete files. We'll then look at ways to write and read to a file, and then we'll explore how to inspect file properties like last modified, for example, and we'll conclude by implementing a file watcher in Go, which basically watches for file changes and report them when they happen. The golden gate to most file operations in Go is in the OS package, which can be found at golang.org/pkg/os. When we visit the package page, we can see the front page starts with an example of how to open a file. We can also see here as an example on how to read a file in Go after we open it. So we can see here that we use os.open to open a file, and we can see it returns a file handler, which we can then use to read the file. We'll cover out in code how to achieve that. Now, to test some code, let's create a new folder called File Handler underneath our Hydra folder, and in there we can create a main.go file. So we can start by opening a file. So, as we have already seen, to open a file, we use the open function from the OS package. And then we put the file name. So by doing this, the open function will return two results. The first one is a file handler. The second one is an error, in case an error occurred. In here, I added a quick error check function, which takes an error as an argument, then checks if it's nil. If it's not nil, then we do a log fatal to log the error, then exit our test program. After we're done using our file, we need to ensure we close our file. So in most programs, we would use defer for that right after the open file code. So by doing defer, then the file close, we ensure that the file will be closed when our function exits. An important remark here is that .open is used to open files for read only. In order to use files for read-write, we will need to use a different strategy. In Go, the file struct represents a file handler. This struct implements methods from various interfaces, like IO reader and IO writer. Because the file struct implements the IO reader and IO writer, as well as the IO closer, the file struct supports the read, write, and close methods. Also, being a child of these interfaces, the file struct is capable of functioning with other packages, a lot of other packages, like FIMT, buff.io. So for example, we can put file type as an argument to fimt.fprint or buff.io.scanner, and so forth. So this allows us to use any reader or writer code with the file struct. So how about creating a new file for writing? In Go, this is a very simple task. We can just use os.create and then supply it with the new file name. And this in effect will create a new file and set the proper flags to allow us to write to it. As usual, we need to work with the error, check the error, and if there's an error, we take an action, And then we need to make sure we clean up resources after we're done with the file. So again, the simplest way to do that is just use defer and then the file name to close. File name here being the file struct object or the file handler, which would represent our file. But what if we want to open a file for both reads and writes? For this, we need to use a more generic function, which is called openFile. openFile allows us to add OS flags and access write flags to associate with our file. So this will allow us to open either existing files for reads and writes, or we can even create a new file with it. So we can see here a list of the OS flags that we can use. The same list exists in the package page for the OS package. So we can see here that we have flags for creation, we have flags for appending to the end of the file, we have flags for read writes, and so forth. And we can just OR flags together in order to get join functionality. The third argument here would be specific access rights based on the owner of the file, the groups, and other users on the computer. So this is similar to how a Unix or a Linux system handles a file. So there would be read and write flags for the different user types. So either owner, groups, or everybody else. As usual, we handle the errors, and then we call defer with file.close method in order to ensure we clean up resources after we're done. So we can find the second argument flags here under constants in the OS package page. The second argument allows us to control very important things like whether we want to truncate, append new data, and so forth. To understand the third argument more, we can just go to the Wikipedia page for file system permissions under numeric notations, and we can see here what the different numbers represent. So 777, for example, would mean read, write, and execute for owner of the file, the groups, or anybody else. And this is, of course, a security risk because it gives access for everybody. There's also 666, which we used in our example, which allows reads and writes for everybody. Perfect. What if we want to rename a file? We can use the os.rename function, which will take two arguments. The first argument would be our current name for the file, and the second argument would be the new name that we seek for this file. And as usual, we check the error using our print fatal error function. How about moving a file? We can actually use the os.rename to also move a file if we want to. So again, it takes two arguments. In this case, we would use relative paths in order to specify where the current file is at and where we would like to move it. So this code effectively will move test1.txt from the current folder to a subfolder called test folder. As usual, we inspect the error afterwards. Now, how about copying a file? So this will get a little bit more involved because Go doesn't have a direct function to copy files. However, it's not difficult to do so. So let's write a function to do that. So we'll write a function called copyFile, which takes two arguments, fname1 and fname2, both of type string. And each of those arguments will represent a file name. So we'll open the first file, fold, and then we'll create the second file, fnew. So again, that's assuming that we want to copy content from fname1 to wherever fname2 is at. And we'll use our error handling whenever we call a package function. And we'll also use defer to ensure we clean up everything that we use. So by doing this, we ensure that the close calls will be stacked together and executed at the end of the copy file function. We will then use a function called io.copy, which belongs to the IO package. And basically what this function does is read from a reader interface, then output its contents to a writer interface. So it will read from fold, and then it will output the contents to fnew. So it basically copies bytes from source, which is the second argument, to destination, which is the first argument. We'll check the errors as usual. And then at the end, when we're done, we will use a method called sync, which stands for synchronization. And this method belongs to the file struct object, and it will flush the copied content on the file objects to disk, so basically to our hard drive. And this effectively will complete the copy. And then we'll check errors as usual. Now, how about deleting a file? This can simply be done by the os.remove function. So we just put the file name and it deletes it. Now, it's time to talk about writing and reading files. So as mentioned earlier, the file types support the IO readers and IO writer interfaces, which means we can do something simple like this and it would work, because this call is supported by the reader interface. So this call will read the file content into a byte buffer. An important package which we can use with files is the ioutil package, which can be found at golang.org/pkja/io/ioutil. The first function to note on this package is the read_all function. So ioutil.readAll. So this function can take a reader type, which in our case, we know that file objects support IO reader interfaces, and it returns everything on it in the form of a byte slice, as well as an error type to represent any error that might have occurred. So basically, we can use this function with a file object which supports the io.reader interface in order to read the entire content of the file in one call. There is even a more direct function that would read an entire file, which is called readFile. So readFile would take a file name, as shown here, as a string, and will return the entire content of the file in a byte slice, as well as an error if an error occurred. So if we look at the code of readFile here, we'll find it similar to what we have seen before. So we can see that we're opening a file. We'll cover the stat here later, but basically we're checking a bunch of stats. And then at the end, we're calling readAll, which we have covered earlier, in order to read all the contents of the file. So if we look at our code, we can see how easy it is to read an entire file by just doing calling ioutil.readFile with the file name, and it will return a bunch of bytes which represent the file contents. So in here, we see here that we had to cast these bytes to a string. So we do that in order to show the representation, like convert the byte slice back to an actual string that we can read. And the string, of course, will be all the contents of the file. Now, what if the file is too large and we want to read it line by line? For this, we will need to use the buffio package, which is very important helper when you seek to scale your code when it comes to file handling. So buffio allows buffered IO operations, so it allows us to work with buffers in memory instead of directly with disk. So the buff IO package exists in golang.org/pkj/buffio. So in there, there's a very important type that we need to cover, which is called scanner. The scanner allows us to scan the content of an IO.reader interface implementer with a lot of flexibility, so we can use it with files. So new scanner would be the constructor, and it takes the IO reader as an input and returns a scanner for us. And then we can use scanner.scan in order to scan the content of the IO reader, which would be our file in this case. So we can scan it line by line using the scanner.scan method. Let's go back to our code and see scanner.scan in action. So we will use F3, which is a file handler which we have created using the os.openFile function. We'll create a new scanner from it using the buffio.newScanner constructor. This will return a scanner type, which we can then use in a for loop. So remember that in Go, there is no while. So for is a keyword used for any loops in Go. So in this case, this will act as a while loop, which will iterate as long as scanner.scan returns true. And scanner.scan will return true as long as the file it's reading still has lines to capture. And then when the file ends, the scanner.scan will return false and will exit the for loop. So in this code, I use a count in order to count the number of lines in the file as we iterate, and we also log the line captured from the file. So in order to log the line, we need to use a method called scanner.text, which will show the current line captured from the file. So this technique would work well with a very large file to handle them line by line. So now let's see how to write some data into a file. So we'll still use the F3 file handler, which we opened as read write with the 666 flag. And we'll use buffio.newWriter in order to get a buffer writer type. So buffio.newWriter can take an IO writer interface type. And because file handlers support IO writer interfaces, same as how they support IO readers and IO closers, we can use it in this constructor. So this will return a write buffer. And then the write buffer supports a method called writeString, which we can use to write a string to the write buffer. Fimpt.sprintln returns a string with the supplied arguments. So it's simple formatting function, similar to the ones we find in other languages. At the end, we must call the flush method in order to flush the contents of the buffer to go to the file type. And that's how we commit our changes to disk. Now let's explore how to inspect file properties in Go. So in the OS package, there's a handy interface called file info, which exposes a lot of properties for a file. So we can see here that we can get the name, size, the file mode bits, last time it was modified, whether it's a directory, and even the underlying data source. So it's worth running the generate file status report function in order for us to see how the output would look like. So I created a new file called check file props to go, which is basically a package main file. And in there, I copied the generate file status report as well as print fiddle error functions. And then in the main function, I just call the generate file status report with a file name which exists in the same folder as our code. So if I now go to the file handler folder and run this code, so go run check file props to go, we will see here the different properties that we've retrieved. So is it a directory? No. The permissions are the ones shown, so only seems like only the owner has the ability to do a write, and the groups and everyone else can only do reads. So the file size is 14, and we see here it's actually 14 bytes. That's true. And the last time the file was modified was in this date. Perfect. So what if we want to implement a file watcher to report when a file change occurs to a certain file? I created a new file called file watcher.go, which we would use in order to implement our file watcher program. And in there's a function called watch file, which we will cover. So in watch file, it will take a file name as an input, so it's a string type. First thing we do is to get the provided file, like file info, to inspect the file properties. If an error occurs, we exit. And then second, we open a continuous for loop in which we will inspect the current status of the file on regular intervals. So by doing that, we'll just sleep, like say, let's assume we'll inspect the status of the file every second. So every second, we will sleep for a second, and then we will call os.stat again on the file, but this time we'll store it in a different variable called filestat2. And then we check the modified time in filestat1 and the modified time in filestat2 and compare them together. And if they're not equal, then we know that the file has been modified. So we report that the file has been modified, and then we update filestat1 with the new status to reflect the current status of the file. And of course, we handle any errors should any occur. So in a production environment, this logic should sit in a Go routine to act like a permanent file watcher. So let's run our code to see it working. So we'll just use go run. So this will run our code, and currently it should be inspecting the file status every second, but there's no change, so it's not logging anything. So in our main function, we supplied testfile.txt, which is this file, as an argument. So this is the file our program is currently watching. So let's open up the file and let's change something. So let's say this is Mina, and let's save the file, and voila, our program captured that the file had been modified. Let's try another change. This is a new line, and we save, and we capture the change again. So let's delete the two new lines and then save, And we capture that as well. Perfect. So our file watcher works as expected. In a production environment, we can then implement special logic to be executed when a file changes.